Oh, good evening, everyone. Thanks, Tanjit and Tapinya, for showing up a bit earlier. I pressed the record button, so there won't be any mess up on the recording, I hope. Okay. So tomorrow we will have another makeup class about the same time, 1.5 hour. That will be the second part to cover the class on Monday, October 17, that we had to trade it to the midterm exam space. Okay, so thank you everyone for joining. And for the team that prepare to present AI application, okay, that includes Tanjit. That will resume when we are back to the regular classroom on site. Okay, so Tanjit should be the next time we on site at CB2306, there will be one more team, and then Tanjit will present another week after that team at 2306. Right. And today agenda, okay, is supposed to be a little bit easy. I just want to go through the fuzzy expert system, especially in the inference process slowly, because in the previous class, I was kind of rushed it, okay? And then if we have time today, I will start the genetic algorithms. But if not, the genetic algorithm will be covered starting from tomorrow. So before going to the fuzzy logic, I just want to remind everyone some more of where we are in comparison to the overview of the entire course. Okay. You can see that in AI class, we highly emphasize the important how to put knowledge into the computer system, okay, because we so well aware that as human we have inclusive knowledge from our upbringing, our learning, our observation that we learned in our childhood to present. Okay, but in human things seem to be at ease and inclusive at time, but when we want to do the same thing or equip that kind of capability to the computing machine, we have to very well thought and design a way to put the structure into the computer system that we aim to be the platform. Okay. And to do so, if you recall at the beginning of the course, we tend to cover a lot of approach in the symbolic. Okay. And you can see that state space search will be in terms of graph as well, and conceptual graph also in terms of the language concepts. Okay, so last. Okay, but you can see that state space search also make use of some kind of graph structure. And we touched a little bit 3 weeks ago in terms of the introduction of how to encode knowledge in either propositional logic or either in the form of predicate logic. Okay. In some of the topic, we might not talk much. Okay. However, the one that we cover, you can see that rules. Okay. We cover a lot, and okay, part of logic. Okay, also there. And rules, the key thing that it's very, very close to human natural language way of conveying our knowledge. Okay, that is in the rules, we have the if, then form. And in AI rules, the rule condition we have special name called antecedent. Pardon my spelling. I think antecedent might be CIDENT, which ante mean before. Okay, and then the result part of the rule is called consequent. And you notice that these are very common form how humans communicate. Okay, for example, if things are too hot, then wait a while before touching it. Okay, so you can see that that's how humans feel very natural to convey and encode knowledge in such a form of rules. Okay, but rules in AI, we also allow the flexibility more. Okay, that is, we allow we can use and or. Okay, in the antecedent. Okay, that help us expand our ability to represent the relationship of the rules condition. Okay, and the same thing can go to the result part as well. It doesn't mean that when the antecedent is true, the result we can only happen only one thing. Okay? It could be more than one consequence. Okay, for example, if patient is detect stage 3 cancer, then the treatment can be surgery plus chemo treatment. Okay, so you can see that the consequence can have two things, okay, or more than one. And to go with the rules, we also learn that before we talking about rule, we talk about how to handle uncertainty. Okay. In that area, we use two major concepts such as naive Bayes and certainty factor theory in Mycin rule-based expert system developed at Stanford in 1970s. Okay, so those are representation, but we can still continue the symbolic method, but this time we provide even more flexibility. Okay, so the level of flexibility become more flexibility by take care of fuzziness. Okay, in the antecedent part. And the same thing can also happen to the consequent as well. Okay, and that's why in the past couple of weeks, okay, we are learning into the area which is a part of expert system, but we call fuzzy expert system. So you can see that the relationship of fuzzy expert system is a form of rule-based still, except that the fuzziness or the fuzzy set theory provide more flexible mechanism to handle that uncertainty. Okay, uncertainty in fuzziness can be in the form of different human have different person have different degree of value, even the same concept, but one person may interpret it in a very high degree, where the other person may interpret the same incident, but in less degree. Okay, so that is a common uncertainty of the interpretation in human. Okay, and since Professor Lotfi-Zadeh and a lot of other fuzzy logic such as Eugenio or Mandani have come up with various ways to model this kind of uncertainty handling with the human symbolic language. Okay, and that stem the fuzzy logic. So to do so, if you recall in the earlier part of the fuzzy logic, okay, in the earlier part of fuzzy logic, you can see that we introduced that kind of the English word that tell various degree of concept. Okay, such as a little bit fast or very fast or kind of slow or medium height or extremely heavy. Okay, so you can see that in the human sense, these are our natural way to convey the description of things around us and rule around us. So we're gonna use the same words, but we're gonna embed it how to deal with this degree of level of concept in a mathematical way, and this will become platform the another option inside the rule-based expert system that we call fuzzy expert system. Okay, so to do so, we start even in the midterm exam, if you recall, we start to find variables of the that could go to the rule antecedent part, but that variable must convey that kind of gray interpretation, you know, partial membership or multi-value logic. And once we start to have input fuzzy variables and output fuzzy variables in a certain expert system idea, okay, then we can model everything using the fuzzy set theory, okay. And you can see that the main concept of fuzzy set is that we allow partial. Things can have full membership with 1.0 designated full membership for that concept, okay? Or thing can be also absolutely have nothing into that membership at all as 0.0. But the key thing to maintain the fuzziness is the somewhere the gray level in between. Okay, for example, this is the graph showing in the real world things of high concept is modeled with the actual height in centimeters measurement. Okay, or in the fuzzy concept is called universe of discourse, right? But we have to define how to come up with such partial. Okay, and to come up with such partial membership, okay, is defined with degree of membership. Okay, and this thing, this shape have a specific name we call membership function. You can see that most membership function is convey partial degree. Okay, and here you can see extremely 0, extremely 1, but convey partial degree in the middle. Okay, and besides that, the important part, you have to map into the real world definition of such concept. What kind of variables you can think of when you think of that concept in the real world, such as the height, the weight, the speed, okay, or in the midterm exam that I have asked you about the concept of overweight. Okay, some of the friends talking about kilogram weight. Okay, some of the friends talking about an index called body mass index, which is the BMI. Okay, for example. Okay, so the universe of discourse could be the real measurement. Okay, or index type value like BMI. Okay, so use your judgment into construction fuzzy expert system, whether what is the best universe of discourse variable of that particular problem. And you can see that the fuzzy set can be 1.0 if it's totally belong to that concept. Or on the contrary, can be totally 0.0 if it is absolutely not in that concept. Okay, but to have fuzziness, okay, to have a fuzziness, what we give more attention to is how to handle things in between. Okay, so this is the core of fuzzy logic. So the partial, you can see that the mu a of x is the one representation on the x-axis. Okay, so that x value in the real world, but the mu a, okay, represent how much degree of membership for that particular concept. Okay, and to start with that, then we can start to define a more through or more detailed fuzzy set that describe the whole concept. Okay, so you can see that in this graph, we have three main concepts: short, okay, and average, and tall. You can see that this part is mu tall of x equal 1, okay, equal 1.0. Similarly, this part is mu short of y, okay, equal 1.0. Okay, you can call x or you can call y, or you can call x2. Okay, either way. Okay, but you know what it means, that it just whatever, if this is the y value, and if this is a certain x value. But the fuzzy part start when you can see that this part onward fully represent the fuzzy concept. Okay, because for example, at this point, you can see that in this, let's say if I call it a Z point, okay, the Z can touch the green shape at this point, but touch the pink line of short at that point. Okay, so Z 167, let's say 167 cm, okay, can have partially about, so 167 cm. Okay, so Z equal this. Okay, so he can be about 0.2 average. Sorry, mu average of Z equals 0.2. Okay, and at the same point of 167, you can see that there is another spot that vertically drawn. It will touch part of the outer rim of the short shape, about 0.6 approximately. So mu of short of Z equals 0.6. Okay. So you can see that that's where the fuzzy logic kicking in. That means certain rule that apply to average shape will take place. But at the same time, there will be another result of certain rule that apply to the short shape, also apply for a different degree, but they both occur at the same time. Okay, and that's why in the inference that we will cover more detail today, that's how we try to handle the the truth, partially truth, of more than 1 degree of membership. Okay, and that signal that we might have to learn to activate different rules in rule base for a different degree. Okay, ES shortened from expert system. Okay, we have to determine of how to fire or activate each rule for a specific degree. Okay, so being fuzzy rule based, we're not going to entirely activate the truth in one rule for the whole rule no more. Rather, we allow the rule based expert system to see whether how many rules involved in those partial truth interpretation. And if there are more than one rule, and we then have to determine whether each rule how truth is true for the antecedent, because that certain rule will be affect into how much degree of the consequence of that first rule will be taken place. Okay, but the same effect can extend to another partial rule in rule 2, rule 3. Okay, so that's why in the fuzzy expert system, okay, so in fuzzy expert system, okay, fuzzy ES, okay, you're gonna have rule 1 if then y equal to, okay, rule 2 if then z equal to, okay, but then rule 3 might say if this is true, then m equal to this and y equal to this. Okay, so you can see that the relationship of inference here, we try to determine, for example, in if something happened and rule 1 is 0.2 true, okay, and rule 3 is 0.5 membership true, just for the condition part. Okay, you can see that this will affect y for a certain degree. Okay, for example, it might affect that y for 0.1, or it might affect y for about 0.3. Okay, so at the end, after the end of the inference cycle, okay, what we are doing is to determine the net final. So at the end of this truth, okay, we are determining the net effect on y. Okay, you can see that the net mean, because here we activate partial firing of rule 1 and rule 3 for the y. Okay, but in this case, the variable m is gonna be affected by just one condition of rule 3. Okay, but in the case of y outcome, y fuzzy output, it will be affected by the firing of rule 1 and rule 3 together. So that means we have to combine the result and make it like the net effect here on y. Okay, so that's the main idea that I kind of quickly show you already last time, but it's kind of rushed. So today we a little bit gonna go a little bit slow on that. So thanks you all for sticking around. Okay, and you can see that to do so, the inference process, Professor Abraham Mandani from London University also come up with the idea of collective effect. Okay, so the style of Mandani will be collect them all. So it's like collect total effect in detail. So that means the effect it's going to be the most accurate. Okay, most accurate in general. This mean most accurate result. But more time consuming. Where the other opposite approach, Sugeno, okay, maybe he have a hint of Japanese. Okay, so you can see that in his style though, Professor Sugeno, see, in the Professor Sugeno, he rather go with simplicity. Okay, go with simplicity. So the same effect, we only collect simple matching matching response, okay, that we defined earlier, okay, and we just tally them. Okay, so the result, this make the result kind of approximate style. Approximate, okay, but quick. And it turned out both approach, okay, from the last class. I just want to tell you like the overview first, and then we'll go into the real example one more time. You can see that with this approximate by the predefined value, okay, it's kind of like a lookup table. So this Sugeno style will give you a very, very fast lookup result tally total. But in comparison to Mandani, it might not be as the most accurate. Okay, but even then, both methods are pretty good in real practical. Good in real use for both options. Okay, so if you be a part of knowledge engineer to help someone construct knowledge base using fuzzy logic expert system, okay, you can see that these two choices often come up on the software, okay, on the software. And to choose which one over which one, it's just a matter of do you have the resource limitation or the time constraint, okay? Because the Mandani being the most accurate will need more computer cycle time to compute, where the Sugeno, because of its short and brief lookup style, it get you a very quick cycle of response, okay? And in some application like engineering controller, they like the practical of quick response, okay, because being fuzzy logic, it means even though it's not accurate, but the intelligent machine or the controller could correct itself in the next cycle of interpretation, okay, because the cycle is so short, it can correct itself next time, while the Mandani still try to figure out the effect on the first round and not finished yet. Okay, so those are the trade-off, okay, in general. But let's look into, for example, okay, how we do it. So you can see that the concept of having rules, okay, are there. Okay, so we still have rules, we still have rule-based, just like the common AI rule base that we've seen before. Okay, we still have rule base to construct. Let's see if I can change. Sorry, probably not good choice. Okay, you still have rule base to go, but the thing that make it fuzzy, you can see that in the start, when you talk to your client, your domain expert, or even the client, okay, that you talk to, they can help you come up with the variable that they put attention to. Okay. The next thing you may ask them in terms of what are the levels of interpretation that they run into. Okay, so here you can see that the project funding is called into 3 different levels. Like the first one is adequate, and the second rule take care of the second level, marginal, and the third rule is talking of the third option level of inadequate or nearly none. Okay, so when you start to have different degree of levels at the same time, then you can start to form, oh, this might fit the fuzzy expert system concept. Okay, and again, being rule-based, it is so natural that you can incorporate the concept or and. Okay, or you can see rule 3 doesn't need the second input variable on the antecedent. That is okay as well. So the being fuzzy rule-based, it's just the extension of the common AI rule-based expert system. Okay, next you have to determine which are the input. Okay, so you can see that the input here is project funding. And so if this is the input 1, project staffing will be input variable 2. And here, let's see the output variable. Okay, you can see that here we only have single output variable, which is the risk. Okay, and also in this example, the risk come to 3 possible levels of either low, normal, or high. Okay, so these definitely very well fit our, the common human natural language communication. Okay. Once we have this, then we convert these English rule into the corresponding kind of like a variable name base, but shortened. Okay, so you can see that project funding is named in X. And the output risk is named as the letter Z in the then part. Okay. And the second fuzzy input of project staffing is called as the variable Y. And then the different levels of each input or output variables is represented by different levels. So you can see that the project funding, that's why you have adequate as A3, you have A2 to represent marginal. And you have level A1 to represent inadequate. Okay. Similarly, the output variable risk seem a lot more straightforward, because risk you have low, normal, high. So you can see that Z is C1, C2, C3. It's just natural mapping here. Okay. So knowledge engineer find the English-like rules on the portion on the right, and then you can start to map into a shorter form of working input and output fuzzy variables, literal, like X, Y, Z, and so on. So the first step, okay, whether you use Mandani or Sugeno style, the first step is the same. That is called fuzzification. Okay, so fuzzification means input as real world values, but the output instead is gonna be the new value or membership values. Okay, so that's the key thing. We try to match whether how true is this real world value convert into the corresponding fuzzy degree of membership function. Okay. So this is straightforward of try to figure out the part of the shape that the x, okay, for example, in this example, x1 landed here. Okay, so again, you can see that the shape, outer perimeter of A1 was there, and another shape was the triangular of A2 concept was there. So in this case, x1 never touched any part of A3. You can see A3 was not touched in any perimeter part by x1. Okay, so that's why here x1 will be interpreted at two spots. The point that it touched A2, which give membership about 0.2, and the part that it touched the edge of A1 concept, which is about 0.5. So that's the first input, determine how true. Okay, so it means the first project funding, okay, is touching to level into different degree. Okay. Same thing go with another variable project staffing. Okay, you can see that project staffing at Y1 also touched at the very base of the B1 shape. So that's why the membership function is very low. Okay, but if you draw vertical line, it also touched another part of B2 shape at that spot, about 0.7. So this determines how true is x1 variable for 2 degree of A1 and A2, okay, and how true is Y1 variable for 2 different degree of B1 and B2. Next, we try to evaluate the complete net effect for one rule. Okay, so rule evaluation, this is per one rule effect. And here you can see that we have two variables. And it depends on the condition on the rule, whether are we talking and or logic. Okay, so again, the reminder, the OR fuzzy operation is very simple. It's a optimism. Okay, so when we talking optimism, when we have many membership to consider, we take the maximum value out of it. So R take the max. And on the contrary, if the fuzzy logic use a more stricter AND operation, okay, the AND would be more pessimistic. Okay, so it only take the mean effect of all the membership values for the same X. Okay, so we can use this to help combine the effect of when you have more than one membership values. Okay. And that's why, that's why when we break down how true is each rule, okay, you can see that rule 1, if X is A3 or Y is B1, okay, but we determine that X never touch A3, okay, so that's why it's 0.0 here. Okay, and because the rule is described the or y is B1, and it turned out that we do have B1 of 0.1 membership true. So with the or, this means the effect of rule 1 will be activated for 0.1, okay, which is the height of this part of the C1 shape of the C1 trapezoid. So nothing much. And we would do the same to check for all these truth value, whether does it apply into some other rule besides rule 1. Okay, so we come down and check the possibility how it touch other truth in other rule. So rule 2 talking about x is A2, okay, which is true for 0.2 degree. And y is B2 for 0.7 degree, which is also true. And this time we have more stricter sense of combine them with n. So that means we are at 0.2 and 0.7. So the 0.2 is the pessimistic minimum between them. And this rule 2 would apply to the effect of C2. Okay. And that's why only the base of C2 is activated for the height of 0.2. And finally, the last rule, we have rule 3. And rule 3 is obviously only applied with just one A1 concept. No need to consider additional input variable. Okay. And we happen to have x1 to be true for 0.5. So that means the effect of rule 3 will be activated 0.5 as well in this portion of C3. So at the end of the falsification, okay, you can see that we have 3 combined effect. The green cross-hatching and the pink cross-hatching and the red cross-hatching combined. Okay, so the next step, we're going to combine the effect of all these 3 rules. Okay, and that's where if we do it Mandani, okay, the effect is called clipping, okay, or scaling. But basically, it just try to find the membership into the common zone and so on when it merge. But the easiest way to aggregate, okay, for example, here we have the effect of rule 1, effect of rule 2, and effect of rule 3. You can see that when we combine them all, we got the result that become shaped like a polygon toward the rightmost. So that's the final result. And because it's a polygon, the general engineering heuristic is like, okay, let's figure out where is the balance point. Okay, and the balance point of any polygon is the best is like a center of gravity of this polygon shape. Okay, and that's where the end result we're gonna return back to the end user. Okay, so that's why the step 4 called defalsification. Sorry, defalsification is mapping or remapping net membership function, okay, to real world output unit, okay, in the real world. Okay, if it were autonomous vehicle, it means what should we put the defalsification into the actual speed of the car. Maybe the car need to slow down from 40 kilometers per hour down to 20 kilometers per hour action, and so on. And the center of gravity, usually it uses the concept of the integral part in the curve shape. Okay, but for the Mandani with the polygon shape, the best approximation, okay, is to calculate each sub-small shape and tally them together. Okay. That is a good approximation that you can get. Maybe not exactly, especially like in that thing, but even then it's pretty close to the complete one. Okay, and that's where the center of gravity by approximation, okay, into the smaller zone of each shape was computed and come out 67.4, which imply that the end result will take shape about this spot to be the center balance. But for Sugeno, if you notice, the singleton act like kind of like a lookup level or lookup table or lookup value. So it's going to be very fast response. Okay, it's going to be very fast response. You can see that the lookup is kind of like when you pass this in, okay, kind of get you. But usually it's a very quick execution lookup value. Okay, lookup value. And even more simpler one, now it's not even a function, but now it's a totally lookup value, not even lookup function. It's a constant. So this one is a lot faster. Constant. The first choice was lookup matching function and execute that quick function, but this option is like not even function, just lookup value and return. Okay, so the return effect act like this height of each possible concept. Okay, for example, rule 1 gonna return K1 for this height. Okay, and rule 2, then K2 gonna return this height of 0.2. Okay. Similarly, rule 3 gonna return C is K3 for this level of height of 0.5. So at the end, okay, you become calculate the average, okay, the average weight average of each height, okay, in the summation. And that amazingly come out quite very close to the most accurate Mandani, very little off, not bad at all for the efficiency it's traded with. So in practical sense, if you are a knowledge engineer and assist your clients in construct fuzzy expert system, okay, you just have to look whether what are your limit. Okay, for example, if your client want the most accurate and no worry of efficiency. Okay, if this is the thing, then the client might pick Mandani. Okay, imagine you are helping the bank create the fuzzy expert system for financial advising. Okay, the bank client. Okay, for something like that. If that the case, maybe the bank want your fuzzy expert system to give the most accurate suggestion to the client. The answer may take some longer time to figure out, but the result is the best performance. Your client can get the most recommendation from the fuzzy finance advisor, whether how he should invest in a certain type of asset, for how much and for how long. In that case, the optimum answer is what requests from the end user without any worry of it might take longer time, something like that. Then you go with Mandani. But if the performance is acceptable, even though it might be a little bit less accurate, but it's acceptable and it's very fast and practical. Okay, then the Sugieno, will be the good approximate choice that quite common. Because again, the efficiency in the Sugieno mean the system itself can correct if it's like fuzzy apply in terms of controller type, controller type, where you put it in the device and the device continue working in the next cycle. So Sugieno tend to be for controller that repeat in next cycle. So Mandani might be suited for thing that only want optimum. But in the example, you can see that the Sugieno was 65 and Mandani was 67.4. So Sugieno wasn't bad at all. Bad at all. And notice that in practicality, these shape I try to show you this seemed quick to you because the shape was in like very polygon. That one is called trapezoidal. In Thai, สี่เหลี่ยมคางหมู and this one is triangular. Triangle, right? So you notice that this shape is very fast executed. To know the x, you can find the linear line relationship. You can decode to get the membership function right away. But keep in mind that the membership function sometimes can be more complex shape, like curve. So in this case, the curve membership function, curve line take longer to get mu value. Because the computer need to compute that complex, the curve line equation. So that's also the consideration of how you define the membership function. But to show you just a simple form, the textbook use the pure polygon like trapezoidal and triangular. But in real life, you also have this type of even more complex curve in the membership function. To consider. So this definitely gonna affect the how long it take. This gonna affect how long it take if you gonna do things perfectly the best using Mandani. You have more overhead in the computation. where the Sugenoo is more like a lookup value or lookup function is a lot faster. So now, I think in the last class, I haven't touched this part. Okay, so that was a review, but here I can show you more. Okay, so you can see that here, the expert system act in the form of recommend decision support, but the behind decision support was backed up by fuzzy expert system. Okay, so service center, okay, car service center need to keep spare part, okay, and their job is to fix the car, okay, fix the car, okay. So customer bring the problem part, and hopefully to get the spare part replaced into his vehicle, okay, and in this information, the failed part may have a return shelf life if it got fixed, and then it can be back into the circulation on shelf and become the future spare. And you can see that when you run the service center of any kind, the common goal is usually you want the manager to be able to balance between how to make the customer happy. And at the same time, the service center does not need to have too many spare parts, because that means the cash flow of the service center is very bad if you have to collect too much of the spare parts sitting on the shelf. So it has to be balanced, but at the same time, you don't want your customers to wait too long all the time. Okay, so it has to be balanced decision. Okay. So to do so, it starts by try to find linguistic variable involved. Okay. And once you find a linguistic variable, it could be both input and it could be output. Okay. I put an S because there could be more than one input variable or one output variable, depend on a certain problem. And then for each fuzzy variable, then we determine the corresponding fuzzy set. And the next rule-based part is we construct a set of rules that use all these linguistic variable and fuzzy set. For example, team A, okay, may use the fuzzy set, the number of spare, okay, but team A might define fuzzy set to just two levels, like medium or large, okay, where team B might look at the same number of spare, but model it in like maybe 3 different levels, like small, medium, large. Okay, so same linguistic variables, but if you create the expert system using different team of knowledge engineer, you can have a different levels of fuzzy set. Okay. Or if you do it yourself, you can start by the most minimum fuzzy set, which is the 2. Okay, 2 fuzzy set. Okay, let me type it. For example, let me draw you just 2. For example, if anything, you have 2 concepts. you can see that the two concepts, the best you can do is you can do this might be concept A1. This might be the concept A2, for example. Or another two concept, you can be strictly polygon in that case. Okay, so you can be like that, and another one is like that. Okay, this also fine as well, like B1 concept, B2. Notice the fuzzy part is you got to have this type of overlap. Of two membership. This is the minimum. If you want more from the minimum, you can have more degree. Okay, so you can have this. So that's 3 level. Or you can have a lot more, like so this is 4 level. So you can see that the more number of shape imply if it were in the controller type AI application like rice cooker, washing machine, refrigerator, motor, air condition, motor, you can see that the more levels mean the machine can have flexibility to handle many fine grain adjustment. Okay, you can have fuzzy in different level more. Okay, so it's a very fine grain approach, more detailed fine grain. Okay, this is more like rough. If some of you drive a car, you can see that the anti-brake system ABS. Okay, for example, if you implemented fuzzy logic controller behind the braking system of ABS, when you have a lot of shape, it implies that the controller have more flexibility in adjusting in different zone better, because you take care the fuzziness in different degree for many more possibility. Where if you do that kind of controller with just these two shapes, there's only one possibility of allow fuzzy adjustment. Okay, so the smoother system tend to have more shape. Okay, so that's the key. Okay, there's no right, absolute right, absolute wrong. Okay, in reality, if you are a knowledge engineer, you make the first version of the system, okay, and test it, test and observe, and maybe and then and adjust. Okay, so that's like the cycle of construct the fuzzy expert system. Okay, especially in the controller type. Controller type. So in this example of car service center, okay, you can see that they start by, okay, this is more real world complicated. So they have a lot of parameter. The first one is M, or average wait time. Okay, so this variable really address the level of service, how the customer will be happy or not in mean delay. Okay. Another one is the repair utilization factor, or the Greek low letter, kind of like a small p, but it's like the Greek low letter. Okay, so this means as the manager of service center, you want the business to run smooth. All part become spare part. Customer request spare part, and you can return that into the fixing for the customer car. Okay, so you want the utilization very high, as much as possible. Okay. But at the same time, you don't want to have too many open service spot, too many. Okay, we call server. Okay, server can be the concept of like you go to the bank, how many tellers, you go to fast food like McDonald's, how many people would take your order. Okay, those are representation of the service provider. Okay, it's not server in the sense of computer server. Okay, so this is also S. That means the manager doesn't want to open up too many server spot, because that deploy the resource of the service center. Okay, and also the one that they want to keep in this case is the number of spare part. Okay, so in this application, the recommender system, expert system, want to manage the spare part as the output. Okay, so you can see that now when they break down the mean delay M, the linguistic in natural speaking, short, very short, medium. Okay, and then that convert to the shorter notation. And that's numeric range. Okay, the normalized mean it usually in the case of 0 and 1.0. Okay, it transforms in this range by the word normalized. And same thing, the number of server S also break down into 3 levels and is shaped accordingly. And the utilization low also have 3 levels. Okay, and you can see that the first round, this knowledge engineer break the number of spare because this is the serious output. So the company want to make sure that they can handle the output in a very fine, detailed manner. So you can notice that the output variable have up to even 7 shapes, 7 linguistic value, or 7 fuzzy membership shapes. And step 2, we define fuzzy logic for each variable. M is 3. Okay, notice 0.3 here for the first shape, and very short. So that's 0.3 there, very short. And notice the second shape, 0.1, 0.5 is short. So it tells you that the base of triangular. Okay, so this notation is usually given to you in the fuzzy logic tool GUI. Okay, when you try to set up the system, you don't need to code everything. You just more like enter the value either in the MATLAB fuzzy logic toolbox or other fuzzy tool, open source tool that you use. Okay, so the second variables, number of server, got 3 shapes, small, medium, large. And the repair utilization got another 3 shape as well. But here, notice the output, number of spare, or N output, which is highly focused because it's the output and you are the manager, you want to respond to the best you can. So the company choose to break that down to 7 shape. Notice the overlap, that's the mask for fuzzy logic. And notice in this area too that you can have, for example, here, you can touch this shape first and then touch second time there. And you can touch the RS shape there too. Okay, so you touch RS there, you touch the M there, and you touch the S there. Okay, so you can see that the concept of fuzzy partial membership function in this spot example can even touch 3 partial shapes, not only 2, but can be even like 3. And now construct fuzzy rule. And to be more practical, they don't want to create a lengthy if-then statement. Instead, they create fuzzy associative memory table. So if you have the rules that consist of 3 input, okay, you can have a table right here. You can see that this is the first variable, second variable, and the inside are the output variable. Okay, so this, because there are 9 cells, right? 9 cells. That means you can have 9 different combination of 3 of variable S and another 3 of variable M. Okay, so you have used 2 rules, two input fuzzy in these rules and affect the output. So that's why it come up 27 combination, because you have 3 here, 3 here, okay, and the output, you can have a lot of them. Okay. So the rule table, okay, can have up to 27 in this case, because you have 3 variable, and each variable is 3 level each, 3 level of S, 3 level of P, 3 level of N. Okay, so that come up with the 27 total possibility of input alone. Okay, and notice the M is the corresponding output. Okay, but here they wrote output before input. And the green is input. Sorry, my ink should be lighter. Because we have 3 input and each input have 3 possible fuzzy levels. Okay, so 3 variable, 3 each. Okay, so that come up to even 27 combination. Okay, and then the knowledge engineer will just interview the service center whether which effect of Y variable should you want for that combination of those 3 input. Okay. Or you can wrote as like if-then statement. Again, if-then statement, that's fine. But you can see that the first loop, they constructed round 1. And in round 1, they only have 12 rules. Okay, even though there could be up to 27 combination, but we can ignore some combination. Okay, so you can see that some rules, like the first 3, only affect 1 variable, 1 input variable. Okay, where from rule 4 to rule 12, the rule get more complicated by involve 2 input variables. Okay, but even then, notice that the output has to be addressed, right? At least you have to cover all the shape of the output. Okay, you have to be able to cover the effect in the output. Okay, but some rule may touch more than one rule. Okay, for example, the S, you can see that the S can be the result of multiple rules. And maybe knowledge engineer try out the result of rule base 1, and with only 12 rules, the performance wasn't that satisfactory. So they can come up and come back and tune the knowledge base in the form of the table or a cube. Okay, so you can see that the table or in 3-dimensional, it become break down into the cube. So the first layer go there. Second layer go into here. Okay, and the third, the third row of cube in the back go there. But now it explain become the cube, so that means the first axis talking about M, the second axis talking about S, okay, and the third axis talking about the low, okay, effect, the third input variable, okay, and the label inside these are output variable. Any of these inside the label stick inside the particular cube is the corresponding output variable. So we can deploy it. You can use any assisted tool. In my time, I use Fuzzy with the MATLAB toolbox, but I'm sure these days you can have a lot of Python or Java tool that do the Fuzzy rule-based expert system. Okay, C++, Pascal, anything you like. But you can see that the effect of the result of rule-based 1, the curve was kind of faster, move down, deep down. Okay, so in the world of decision support or controller, it's kind of like your controller wasn't so smooth. But when you compare the decision of rule base 1 of 12 rules and decision that come from rule base 2 of 27 rules, you can see that there were improvement of some adjusting. Okay, they're more crisp, okay, more intermediate kind of angle of adjusting there. Okay, this means rule base number 2, which has a lot more rules, mean it's more smoother. It's not like an abrupt change of response of the system. So a lot more smoother. And you can see that we can even still feel like rule base 2 is still not as smooth as we hope, even though it's already improved from rule base 1. And notice that now knowledge engineer even work out the third cycle, create more rules in the rule base number 3. And you can notice that the cube has now for the S variable from 3 labels, not label, change to 5 labels in this S exit. Okay, so that's why the cube is not symmetrical cube no more, but the variable M and variable low still 3, but the variable S is break down to 5. Okay, and that implies that the rule base have more smoother effect. Even so, you can see that more kind of a tiny angular adjustment. Okay, so these are the part of tuning fuzzy system. So in real life, as a knowledge engineer, you push out the first cycle of the rule base, and you and your client may evaluate the outcome of the first cycle together. If not, then you go back and go tune to have more rules or adjust more levels of fuzzy membership function to be more refined with more labels. So once you have this, hopefully when you are looking at fuzzy exercise, okay, that I gave you 2 weeks ago. Sorry, I didn't have the file here, but you can see that that's why a lot of daily device like refrigerator, controller, the washing machine, the rice cooker, okay, the air condition, okay, the car ABS, anti-brake system, and so on. And a lot of cars, luxury cars inside system is highly software driven with fuzzy logic as well. Okay, so that's it for today, and thanks for hanging out with me and joining. Any question on the chat? Sorry, I didn't type much on the chat. Any question? I hope I go over a bit slow today, but it's should clear more of now. And let me see, for a quick study, I think I didn't show it here, but you can get it from this example. Okay. So fuzzy logic can be applied to controller or can be applied to decision support. Okay, for example, you can create expert system to advising people how to make investment, how to diversify their cash, their mutual fund, their stock, their gold, their real estate. Okay, so those are like parameters for a person to manage for the optimum investment growth goal that the person has. Okay, so you can go with the financial advisor and help create all these rules. Okay. So that's it for today, and then tomorrow I'll be introduce you to more a new kind of genetic algorithm. Okay. For example, tomorrow will be genetic algorithm. Okay. And sometime after that will be genetic programming and neural network, which is more like a more contemporary move of AI. Okay, but it doesn't mean that symbolic AI is no longer used. It's still around us. Okay, around us. It just developed more solid some years ago. Okay, but even neural network, the original was starting in 1943 as well, but the more advanced and more effective, more powerful model are more done recent in comparison to symbolic approach. So I guess I'll end tonight, and thank you very much, and good luck in preparing a lot of other exam next week. All right. Any question? Thank you so much for hanging out with me. Thank you. Bye bye.